section, still going to look at exponential and logarithmic functions, but just some applications for them where they're actually used outside of math classroom. Why do we even bother with it? It's not, there are a lot of uses that come up in the sciences. One of them is for calculating pH. So you guys know what pH is. Talked about that in your science classes. You know, if it's less than 7, it's an acid. Greater than 7 is a base. So pH is actually calculated with a log. It's a negative log of H3O+, which is a hydronium ion concentration. Anything that I do today, I wouldn't, well, I guess you don't necessarily have to worry about the test because we've already done the test over this chapter, but the final or wherever I might put these questions, I wouldn't ask you to memorize any of these formulas. I would give them to you. You just have to be able to use them. So this is the formula for calculating pH. So the first example, I want to find the pH of a solution with a hydronium ion concentration of 2.5 times 10 to the negative 4. So from our formula, pH is a negative log of this. The H3O plus is usually written in scientific notation like that. So now we just put it in our calculator. So we do the negative, the log, and type in 2.5 times 10 to the negative. pH we typically round to 1 decimal place. What'd you get? 3.6021. So we'll just round it to 1 decimal, call it 3.6 for our pH. So B, this time I'm flipping it around. I'm asking you to find the hydronium ion concentration of a solution with a pH of 7.1. So we plug that in for the pH. And we're looking for this H3O plus in our formula. What would we have to do here? Divide by negative 1. Okay. How do I get rid of that log? Think back to those equations that you were solving on your test. How do we solve something like this?
Put it in the other format.
Yeah, move it into exponential form. What's the base of this log? Well, that's the argument. Yeah, if I don't have a base written, it's assumed to be 10. So it'd be 10 to the negative 7.1 power equals the H3O plus. So and that gives us 7.94. At the end, it has E negative 8, so that's times 10 to the negative 8 power. Because that's all usually always written in scientific notation. Right. Any questions on pH? Whether you have to solve for the pH or the H3O plus. Another place where we see these logs is with exponential growth and decay. With that, the function A of t, meaning the amount at a given time, is your beginning amount times e to the kt power. If your k is greater than 0, so if you have a positive that will be exponential growth. You will be gaining over time. If it's a negative, that will lead to decay. So there would be less as time goes on. So just to kind of recap, the A of t is the amount at time t. A sub 0 is the beginning amount. K is some constant, and we have to have that value. And t is the time that has passed. So let's look at an example of that. With these, we'll have to try to create the equation. In the equation, you have to have that a sub 0 and the k value. E is just a number on our calculator. The t is the variable that we'll keep in there. So if 800 grams of a radioactive substance are present initially, and 2.5 years later only 400 grams remain, how much of the substance would be present after 4 years? So my formula, the amount at any given point in time, is the beginning amount times e to the kt power. We have to know the a sub 0 and the k. So we get our equation. My a sub 0, how much did we begin with? Did I give you the k value, the constant? No. But I did give you some information to find it, because I told you at a given point in time how much we had left. So my amount at that time was 400. Here I said a sub 0 is 800. And that was at the point when my t was 2.5. Okay, so I could divide by my 800. And our whole goal here is to find that k value. What would we do now?
With the natural value.
What happens when you have a natural log and an e? So that gives us 2.5k. So we divide by 2.5. So we have the natural log of 1/2 divided by 2.5. So now we have our k. So our actual equation. All of this was just work to get my equation. My beginning amount is 800, e to the kt, so negative 0.2773 t. That's the actual equation we are going to use. So, if I want to know how much would be present after 4 years, you're just plugging in a 4 for your time. And you can just do that on the calculator.
63.86 grams.
I think you guys should try the next one. We have 600 grams initially, so that's our A sub 0. So the equation is the beginning amount times e to the kt. We need k, so we can use the other value given. In 3 years, you have 300. So the amount is 300 equals 600 e to the k times 3 power. And this is sometimes called the half-life. It took 3 years to have half of what we started with. So if you've ever heard that term half-life, that's where it comes from. So to get rid of the e, we add our natural log on each side. Those cancel. Divide by 3. And we get a k of negative 0.23. So now we know the full equation. So then the question is, how much will be present after 6 years? So you plug in your 6. And that gave us the 150.044. All right. Questions there? Another place where we see these exponential equations, we've done interest before. Remember the compound interest formula had an e in it? So depending on what we're trying to solve for, we might end up with logs in those. So our compound interest formula. Did I put that on the front? Yeah. So I did give you guys at the front just kind of like boxes with all the important formulas, and I have your compound interest or continuous compounding formula there. So that is our A equals PE to the RT. So we want to know how long it will take for the money in an account that's compounded continuously at 5.75% to double. Okay. This is my rate. We always have to change it to decimal format, so 0.0575. Did I tell you how much you were going to start with? So what do I do? Okay, what number do you want? Then if I'm going to end and I want to double it, how much do we end with? And we're trying to find the time here. So my A is 200 equals 100 e the r times t power. So to get to that t value, we have to do what? So we can add our natural log on each side. A natural log and an e cancel. So we divide. Remember, this time is always in years. Any questions on that one? I want you guys to try to set up the second one. You'll have to watch though, is that one a continuous compounding? No, so you have to use the other compound interest formula. So what does the 1,000 represent? 2% would be the R. Compounded quarterly, so how many times a year? Okay, we're ending with 2,700, so that's our future value or the final amount. So if we plug in, and we're solving for t. So we divide by the 1,000. 1 plus 0.02 divided by 4. 1.005. Now what do we do?
Divide by 1.005.
Well, that's the base though.
I'm turning to log.
What I would do is add a log on each side. It's like the previous problems where we are adding ln. Because my base isn't e, you could do the regular log or the ln. It's not going to matter. Nothing is going to cancel. But properties of logs, what can you do with your exponent? So we divide by the 4 log 1.005. We talked about sometimes these can be tricky to plug in, so if you need to, you could do the alpha and then put it in as a fraction so you can see that fraction on your calculator. So we should get 49.787 years. Is that okay? The final thing I wanted to talk about is the change of base formula. So I think that's on the front. Log base A of m, you can change to any base you want by doing log of the argument divided by log of the current base. The reason this works is if I said like log base 2 of 3. Okay. Our calculator, and yes, I know there is a way that you can get it to do the different bases, but not all calculators have that option. So the readily available options are log base 10 and natural log, right? If I asked you to evaluate this, you would probably set it equal to x, and then you could do the definition, say 2 to the x power equals 3. Do we know 2 to what power equals 3? So then we would add our logs, and we would do like a log base 10 or a natural log since we have those calculators. And then what happens to your x? And so then to get x by itself, you end up with log of the argument divided by log of the base to begin with. So that's why this formula works from if you were to change it into exponential and then work it out. If I asked you to do this, because I know there are ways on the calculator to get around it, I would require work on this. So when I say work, I just want you to write out the formula if you are going to evaluate one. So if I said approximate this to 4 decimal places, your work would be to say log of the argument, so that's log of 7, divided by log of the base. Log of the big number divided by log of the small number. And then we type that in. And we have it. If you do the natural log, you get the exact same thing. So it doesn't matter, but you need to change it to one of those two. So how would I set up this one? So that's the work that I would require. And we get 3.3219. Try the last two on your own. Oh, that's it? Okay. We're going to stop there then. I have more, but if I don't need them.